Evening. I'm going to continue to solve more questions on single phase transformers. We're going to be looking at exercise 1.1. It's only 4 questions, so without any waste of time, let's look at the first question. Okay. Question number 1 says, a current carrying conductor is situated at right angles to a uniform magnetic field having a density of 0.5 Tesla. Calculate the force in Newton meter length of the conductor when the current is 300 ampere. Okay. So we are told that we must calculate the force in Newton per meter length. Okay. Newton per meter length. So I always said whenever you are about to solve a problem, you must always write the values that you are given. Okay, so let's write the values that we're given. We're given B 0.5 Tesla. Okay, we're given the current is 300 ampere. Okay, so these are the values that we're given, and then we are told to find the force in Newton per meter length. So it's gonna be like this. Okay, because it's Newton per meter length. Newton for the force, and then meter length for the length. So it's force in Newton per meter length. Okay, so we know that the magnetomotive force, or the force that they're looking for, can also be expressed as B I the length. Okay, the length. All right, so because we know that they're looking for force in Newton per meter length, so we can divide both sides by the length. Okay, divide both sides by the length. So we have F over L is equals to B times I. Okay, so this is what they're looking for. So we can find, and we can substitute everything that we have. For B, we have 0.5 multiplied by 300. So it gives us 150 Newton per meter length. Okay, so this is the first question. Okay, this is how they want us to calculate the question in Newton per meter length. Okay, we know that the force is measured in newtons. Yeah. Okay, so in this case it's Newton per meter length. Okay, that's the first question. So we're done with the first question. So for question 2, we can go to the second question. Okay, the second question says calculate the current in the conductor referred to above, meaning referred to the first question. Okay, when the force per meter length of the conductor is 15 newtons. Okay, listen to this. When the force per meter length, okay, when F over L is equals to 15 newton. Okay, so everything is still as it was. B is still equals to 0.5 T. Okay, it's still equals to 0.5 T. So we are told to find the current in this case. So we assume the current is not given. So because it's a new condition that they're giving us. So again, we want to say F over L, which is equals to B times I. So in this case, we're going to make I the subject of the formula. Okay, so we can simply substitute everything, okay, so that it doesn't get complicated. So F over L, I'm going to say is 15, okay, is equals to 0.5 times I. So I'm going to say I is equals to 15 over 0.5. Okay, so therefore I is equals to 30 ampere. Okay, so this is my second question. Okay, this is I believe this is straightforward. Okay, because you're just substituting everything that you're given, but it's very much important for you to understand the question and what they're saying. Okay, so far we managed to solve question 1 and question 2. Okay, so I'm gonna give some time for whoever's watching to digest and to copy whatever that they see if they're copying. Okay, yes, I'm gonna design space. Yes. To move to question 3 and 4. Okay, so I hope I can erase everything and continue. Okay, I hope so. All right, let's move to question 3. Let's move to question 3. Okay. Okay, question 3. Question 3 says the coil of a moving coil loudspeaker has a mean diameter of 30 mm and is wound with 800 turns. It is situated in a radial magnetic field of 0.5 Tesla. Calculate the force on the coil when the current is 12 milliamps. Okay, like I said, always write down the given values. Okay, so we're given mean diameter, d mean of 30 millimeter, and then we're given the number of turns that are 800. We're given the flux density 0.5 Tesla. We're given the current through the coil, which is 12 milliamps. Okay, so for us to calculate the force, we're going to use the equation F is equals to B I L. Okay, so as you can see, we have the B, we have the I, but we do not have the length. Okay, the length, this is the length of a coil. It's the length of a coil. It's L. Okay, the length of a coil, it's L. It's the L that you see in this equation. So that's what we need. That is the known, something that we need for us to be able to calculate the force. Okay, so before we go deeper into solving the question, so they're telling us that we have a coil of a moving coil loudspeaker. So let me draw a coil so that I can easily explain. Okay, let's say this is a coil that they're talking about. Okay, so we know that this coil must have a length. Okay, it must have a length. So this length, okay, let me draw it nicely. Okay, this is the L that we need to find. Okay, but we know that the diameter inside 110. Okay, let me say this is 110. This is 110. Okay, it is 110. So the diameter inside the 110, which is this, the diameter inside 110, that diameter inside 110, it's called mean diameter. Okay, so it's called mean diameter. It's what we're given. Okay, so every time we see mean diameter while we are solving questions related to coils, we remember an equation that says L is equal to pi times D, mean diameter. Okay, L is equal to pi times pi times d mean diameter. Okay, so as you can see, this L is not the same as this L. This one is a straight L. Okay, so what is the difference? Okay, if I take that 110, okay, inside the coil, if I take 110 inside the coil, let's say this is a 10, this is a start, let's say this is the finish of the 10. Okay, so the length inside 110 from here, the length until the other side, if I take this 110 and make it a straight wire, okay, if I take it and make it a straight out, the length of that wire in 110 is L. It is the L. Okay, this is the L that you see in this equation. So remember, I said the diameter inside 110 is mean diameter. So just that I haven't drawn it well, Mara. In each and every 10, the mean diameter is the same. Okay, the mean diameter is the same in each and every 10. So if you assume 110, and then you take the length inside 110, the length inside 110, this is 110. So if this 110, we can make it straight. If we make it straight, meaning the length of this 110 is the L that we're talking about. Okay, so right now we are told that the coil has 800 turns. So we know that the coil has 800 turns, meaning after knowing the length after knowing the length inside 110, so we will simply repeat it 800 times. Okay, we'll simply repeat it 800 times, meaning we're going to multiply it by 800. Okay, so that length in 110 we're going to multiply it by 800. So meaning it's going to give us the total length, which is the length that we want, the L that we want, which is the length of the coil. Okay, so we're going to have the length of the coil is equals to the L times number of turns, which is 800. These are the two equations we're going to use. Okay, so we want to see the length in 110 repeated 800 times to give us the total length. Okay, so this is what's going on with this question. So I hope my explanation makes sense. Okay, I hope it makes sense. All right, so if people understand, so let's continue and calculate. Okay, let's continue and calculate. I'll have to erase everything and rewrite it. Okay, all right. All right. All right. So I said we're gonna use L is equals to pi d mean. Okay. So L is equals to pi into 30 times 10 negative 3, which gives us 30 times 10 negative 3. 94. It gives us 94.248 millimeter. Okay, so this tells us that inside 110 of our coil, the length of 110, the L, is this. Okay, so for us to have the total length, we're gonna have to take this length in 110 and repeat it 800 times to form a coil that has 800 turns. Okay, so for us to form a coil that has 800 turns, we'll have to repeat this length 800 times. Okay, so now we're gonna say the L that we want, it's equals to L times number of turns. So this L gives us, it's 94.248 times 10 negative 3 into 800. Therefore, our length is equals to, let's see, okay, this gives us 75.398 meter. Okay, so now we know the so now we know the length of our coil, the coil that we are dealing with. Okay, so now we know the length. So what we're gonna do, we're gonna calculate the force. Okay, we're gonna calculate the force. Okay, so we know that we have a coil that has 800 turns, and the length of that coil is 75.398 meter. Okay, this is the length of our coil. So F is equals to B I L. So now we calculate the force that they want. So we know that the B that we're gonna use, it's 0.5. Okay, 0.5, and then our I, it's 12 times 10 negative 3, and then our L, we calculated the L, it's 75.398. So therefore our force is equals to, let's calculate, okay, this gives us 0.452 newtons. Okay, as you can see in the problem, there's also answers provided on the side of the question. So for number 3, the answer is 0.452, which is the same thing that we got. Okay, it's the same thing that we got. So as you can see, alright, so that's how you tackle the question. Okay, machines is not that difficult. Question 4 says, two coils A and B are wound on the same iron core. There are 300 turns on A and 2800 turns on B. A current of 4 ampere in coil A produces a flux of 800 microweber in the core. If the current is reversed in 20 milliseconds, calculate the average induced EMF in coils A and B. Alright, coil A and then coil B. N is equals to 300. N is N2, this is N1, 2800. The flux is 800 microweber. So we're given the I is equals to 4 amperes, and then we're given the time T, which is 20 milliseconds. Okay. All right. So we're told that the current is reversed in 20 milliseconds. So this is the reversal time, and we know that what the flux does, it goes to maximum and then it goes to minimum. So it goes to positive axis maximum and then it reverses, it goes to minimum. When it gets to minimum, it reverses again, it goes back to maximum. So it keeps playing through that. So the time that it takes for you to do that is 20 milliseconds. There's the reversal time. Okay, so we know that the maximum flux is positive and then the minimum flux is negative, but the magnitude is the same. The magnitude of the flux will be the same. So already, because we are told about time, we know that we come back to the equation of the induced EMF, change of flux with time. Okay, so the change of flux is considered with time in this equation. So let's calculate for coil A. Okay, for A, so we have the induced EMF negative because it's opposite. Okay, and then A is 300. Okay, and then this is change of, so it's gonna be final minus minimum. Okay, so the final, which is the maximum flux, is positive 800, and then it's minus the minimum, which is negative 800. Okay, and then this is minus 6 because it's micro. Okay, it's micro, so divided by the time of the reversal, which is 20 times 10 minus 3. So the induced EMF for A is equals to, okay, let's calculate 300 okay, I'm busy calculating here. Okay, I'm calculating. So I'm getting negative 24 volts. Okay, or 24 volts opposite. Okay, so don't be confused about by the negative because it's induced EMF, it's opposite. So this negative is for direction. Okay, so we got the one for A. Yeah, we got the one for A. So now we can calculate the one for B. Okay, the induced EMF for B minus NB, change of flux, change of time. So this is negative 2800 final minus minimum 800 times 10 negative 6. Okay, E for B, therefore induced EMF for B is equals to minus 224 volts or 224 volts opposite. Okay, so this is how you solve the problems. Okay, so I don't think that was that much complicated. Okay, so we've come to the end of solving the 4 questions for single phase transformers. Okay, exercise 1.1. So I thank you for your cooperation. I thank you so much. Take care. Thank you. So let's meet on the next lesson.